So to begin this presentation, I'm going to start by showing you a couple of paintings, all done by this artist, very underground, that you may have heard of, Claude Monet. And you might be wondering, this is a science presentation. Why are you showing paintings? Is this like Art History 101? Just bear with me for a second. And so, let's start with the first painting. So this might be kind of what you think of when you think of Monet, right? Think of this as kind of like a control painting. And as you look at these paintings, you don't really have to focus on the minute details. Focus more on how the artist, Monet in this case, is portraying light, the sky, and the general atmosphere of the painting. So now that you've had a couple of seconds to look at this one, again, think of this as the control. Let's move on to this one. And so you can see the river and all the buildings that you can see right there. And again, focus more on the sky, focus more on the air. And then let's go on to our last painting right here, Charing Cross Bridge. So let's take just a couple of seconds to really internalize that painting. Okay. So now that you've had time to really analyze and dig into those paintings, let's compare and contrast the third and the second paintings. And so you can see them side by side here. And so what are some things that you notice? Well, one thing is maybe you notice that time is moving from left to right. You can see that the painting on the left was created in 1871 and the painting on the right in 1901. Another thing that you might be noticing is that the contrast between these two paintings is pretty large, no pun intended. If you look at the second painting, you might notice that there's a lot less contrast relative to the first one. And so this is potentially not unintentional. What you see here is that some researchers believe that the difference in contrast between these two paintings may actually be due to the air pollution in the scene that Monet is depicting. And so Monet really loved this fog. In fact, there's this one quote that I really love. "I adore London, it's a mass, it's a whole, and it's so simple, but what I love more than anything in London is the fog." It's really, really cool, and I guess it shows, that it was really intentional when he's depicting all this low contrast imagery. And this fog wasn't just relegated to Monet and his paintings. Charles Dickens, another author you may have heard of, actually said that it was a foggy day in London and the fog was heavy and dark. And so it seems like this fog is really important when we look at history and art, and maybe it's connected to some of the historical events that were happening in London during this time. And so it turns out that is the case. So all of this London fog is not actually the fog that you might see, on an early morning, really cold, maybe blanketing the mountains, but it was actually pollution caused by coal combustion. And what you can see here is coal miners on the left, and coal has a lot of sulfur impurities. And so when we take that coal from the ground and burn it to create energy, what happens is that the sulfur actually gets into the atmosphere and creates these little small particles that impede our vision and thus create this low contrast. You might be thinking, we don't really burn that much coal now. We use other sources of energy, and that is true to an extent. But that does not mean that air pollution is a thing of the past. So on the left, we have that London fog, right, which is made up of sulfur and tiny particles created from that sulfur. And on the right, you have a picture showing kind of modern day air pollution. And so this isn't caused by coal combustion in a sense. It's actually smog, which is created from ozone and other little small particles. And these are really bad to breathe in, because since ozone is very irritating to your lungs, and those small particles can actually be small enough so that they get into your lungs and also your blood vessels, which not a good thing. And you might be wondering, okay, what city am I portraying in this case? What area is that picture taken from? And so if you guessed California, you are correct. And so California, in the United States at least, is a hotspot for a lot of this air pollution. What you see on the map is the number of unhealthy days in 2016 that certain California counties experienced. And if you look on the dark red counties, they represent areas that could have more than 100 days of unhealthy air in a single year. That's more than basically 1/3 of the year. And so This is a really important issue, especially given the health impacts of having those little small particles go into your lungs and your blood vessels. And the reason why I think about this a lot, and the reason why this topic of air pollution is something I think about a lot, is because I grew up in California. And so right here you can see where I grew up, which is Merced in Sacramento, California, right in the middle of the Central Valley. And I put a picture of a cow because I think that really exemplifies that region super well. And then I went to UCLA for college, which is a college in Los Angeles, I guess, in case there's any Bruins in the audience right here. And that was actually where I took that picture. You can see the Los Angeles skyline from the near UCLA region. And you can see that lovely layer of surface ozone, or smog, and all those tiny particles that are impeding our visibility. And so here are some other pictures that I've taken during my time at Los Angeles. On the left, you see Los Angeles, best seen from Hollywood, so if you're kind of north of Los Angeles looking south. And then on the right, we have another picture of a different area, Coachella Valley and the Salton Sea, which is even more south of Los Angeles. And you see that lovely kind of yellow-brown haze that we love to see during those late afternoons. And so you might be wondering, there's clearly air pollution happening in California. What is the reason, right? In Seattle, we typically don't get this air pollution as much as we do in California. And so why is that? Let's go through some reasons, and this is not a comprehensive list, but I'll just go over 4. The first is that the mountain basins in California can trap pollutants. I mean, California has the Central Valley, right, and has so many mountains, and it causes all of these valleys to maybe have a bit more stagnant air. If air gets at the bottom of a valley, what happens is that it can't be ventilated. The winds can't reach there. And so what happens is now these pollutants kind of build up over time and potentially create some of this pollution. Another reason is heat. If you think about California, you probably think of like the sunny beaches and Los Angeles being like sunny all the time, and that is true to an extent. But all this heat is really important because all of this ozone comes from chemical reactions. If we increase the temperature of these chemical reactions, we can cause them to go faster and faster and faster. And because those reactions go faster, we produce more ozone and thus more air pollution. And so to really drive in that point, I put a picture of a Los Angeles sun right there. Another reason is cars. So you have the 405 here, which is a very notorious highway close to UCLA. And what you have is a lot of these cars kind of in traffic, and they're burning a lot of fuel. And when we burn a lot of fuel, we release a lot of pollutants into the atmosphere, and coupled with the heat and coupled with the valleys, we get a bunch of pollution in those areas. But my 4th reason might be a bit more surprising. Maybe trees are contributing to some of this air pollution. And you might be thinking, that sounds really weird. You might have heard that trees clean the air, and that is true to an extent, but a different process actually causes trees to contribute to air pollution and cause it to get worse. And so this process was the reason why Ronald Reagan, again, you may have heard of him, back in 1981, claimed that trees contribute more pollution than automobiles do. And this statement was received with a lot of op-eds. Here's one that says, "Does Reagan still fear killer trees?" And I put a killer tree right there just to really drive home that point. But was Reagan right? Is he missing some very important details? And so what Reagan was talking about was this molecule called isoprene, which you can see in the middle of the graph. This molecule is emitted by certain trees, not all trees, so in particular oak trees as well as palm trees. And so when these trees emit this isoprene, they actually emit it in quite large amounts. So huge amounts of isoprene are emitted on a global scale. I want to make the really important point that isoprene alone is not toxic to humans and is not technically a pollutant. You can breathe in isoprene and not have any significant side effects. But there's a particular process that can contribute to pollution through isoprene. And so what we're going to do is we're going to kind of step through this process and introduce all the super cool main characters in this process. So first, here are the 3 main characters. We have isoprene, obviously. But we also have something called the hydroxyl radical, and we also have nitrogen oxides. Think of this as kind of making a potion. You can't make a potion with one ingredient, although I'm sure there's some, right? But typically with potions, you add one ingredient, another ingredient, and you stir it all up. That's similar to what happens in the atmosphere. And so you need all three of those ingredients to create the pollution that Reagan is describing. And so the process goes like this. Think of the atmosphere as a washing machine. I guess it's very, very, simplistic, but pretend with me that that is a washing machine. And so you can think of molecules that we emit, like isoprene, as maybe stains on a shirt. And so, right, when we put stuff into a washing machine, we remove those stains. And this is kind of like the cleaning power of the atmosphere. This is a good process because we don't want things to build up in the atmosphere. That's really bad. They'll grow to really high concentrations, not super good. And so what happens is that we can put those molecules into the atmosphere when we emit them, similar to putting clothes in a washing machine. All right, so we put the clothes, those stained clothes in the washing machine. Now, we can't just run the washing machine without anything else. We also need to put in detergent. And so here's 2 Tide Pods here. And maybe use Tide Pods, maybe use liquid detergent. But in this case, those 2 Tide Pods refer to OH, that hydroxyl radical. And so OH is a very reactive species. And so it's kind of similar to bleach in a way. It will kind of destroy other molecules. And so what happens is that we put in that Tide Pod into the washing machine, and it will do the role of detergent. It will start to break the isoprene down. Now, we also need the third thing, right? And that's the NO and the NO2, the nitrogen oxides. And so you can kind of think of this as like fabric softener, right? It's something that you also put into the washing machine to kind of help out, to make the clothes more soft when they come out. And so let's also put that in, kind of like, again, putting everything into a potion and seeing what comes. And so we put in that fabric softener, and let's run it for a couple of hours. So we start with 2, 1, and now it's done. And so now we have clean clothes. The isoprene, which again was non-toxic, it just broke down and turned into some other things, which again is a good part of the atmosphere or self-cleaning. But if you know anything about laundry machines, you probably know that fabric softener is probably not the best thing to put into a machine. Now, I'm not a laundry expert, so don't take it, as an expert talking. But there are instances where putting fabric softener a lot causes kind of this really gunky buildup in your washing machine and the drains that connect your washing machine to everything else, which is pretty bad, and you definitely don't want to have these. And so putting in that fabric softener is kind of similar to putting in those nitrogen oxides. You put those into the atmosphere, and you get this gunk, you get this buildup, and that's essentially the yellow-brown haze that you see, that lovely, lovely smog. And where do these nitrogen oxides come from, right? We know that isoprene comes from trees, but the nitrogen oxides are not from trees. They're largely from cars. And so the car exhaust creates those nitrogen oxides, which then reacts with the isoprene. And what this means is that trees cannot create ozone on their own. They need something else, which in this case is cars. But the most important thing is that the molecules like isoprene, breaking down through this detergent, is what is required to begin the process. And so without these molecules like isoprene that are made from trees, you really can't start this wash cycle. And so looking back at Reagan's quote, right, that trees contribute more pollution than automobiles do, what we can say is that he vastly oversimplified the science, because isoprene alone doesn't contribute to pollution, but isoprene contributes to pollution in the presence of these cars, which are under our control, right? We have control over those. And the implications of isoprene are pretty profound. So here's a map showing the concentration of very small particles. These are small particles suspended into the air, think pollution. And a lot of the isoprene in the US is emitted in this kind of rounded blue box. And so we can say, okay, most of the particles that we see in this map are a result of this washing machine effect, where isoprene goes into the washing machine, it's broken down, and creates these small particles. So we're breathing in these small particles, so maybe how will that impact human health, right? We don't want to breathe in these particles because they can get into our lungs and our bloodstream. And so take a minute and just think about how you expect diseases like heart disease to kind of co-locate with these small particles. And so if you guessed, they're very similar, you are correct. And so what you can see here is that the concentration of these small particles created from isoprene kind of co-locate or correlated with the amount of cardiovascular and respiratory disease that is seen in the US. And so what we know from this section is that isoprene is clearly very important in understanding and predicting air pollution. We have this mechanism right here with the washing machine that can turn isoprene into ozone and small particles, right, that lovely pollution, and that pollution can cause human health effects on a country scale. And so now you're probably thinking, why are the plants emitting isoprene in the first place? And that is a really good question, because if you think about it, these plants are emitting large quantities of this molecule and all of this carbon that they could be using for literally anything else. They could be using this carbon to create new leaves, new branches, maybe new roots, all that fun stuff. And so perhaps there has to be this evolutionary reason why plants are emitting this isoprene in the first place. And I guess spoiler alert, it's a mystery, unfortunately. But we do have some observations that can kind of give us insight into what is actually happening. The first is that we know that intense light can actually increase isoprene emissions. So we have the sun here to really exemplify that light. And if you think about it, plants also need light for another completely different thing, right? Photosynthesis, to create the sugars. And so perhaps this relationship between light and isoprene is pointing at some connection between photosynthesis in the plant and isoprene emissions. That connection is not super well understood, but perhaps there is something there. The second observation is that temperatures also correlate with isoprene emissions. When we increase the temperatures, when we make the plant really hot, what happens is that isoprene emissions also increase. Think of it as kind of like the plant sweating out large amounts of isoprene on really hot days. And perhaps, since temperatures seem to cause isoprene emissions, maybe isoprene is doing something to help protect the plant from heat stress, right? When it gets really hot, that isoprene is produced, and it's doing something in the plant to protect those membranes, to protect all that machinery from further damage. But the implications of this are pretty important in the atmosphere. So as we zoom out from the plant to the atmosphere scale, we have to consider how temperatures on Earth are changing. So here we see global mean surface temperatures, and you can see that over the past couple of decades, the temperatures have been increasing quite a bit. And just as a reminder, this global mean surface temperature increase is largely due to warming, due to greenhouse gases like carbon dioxide and methane. And so one hypothesis that you might be having is that, okay, temperatures are increasing, so maybe isoprene emissions are increasing as well. And so this is where my research comes in. I use satellite observations of isoprene to really test those hypotheses and to really determine what is isoprene doing in the atmosphere and what will it do in the future. And so here's a schematic of what I use. So there's a satellite that's orbiting the Earth, and it's looking down, and it can essentially tell us how much isoprene is located above a certain point at any given time. And so using those observations, we think that more isoprene can impact air quality, but it can actually affect more than just air quality. And it does this through this process. So methane, right, is that one of the greenhouse gases that was responsible for this temperature increase. And if we increase isoprene, there might be an interaction between the two. So if you notice, there's methane on the left and isoprene on the right. And they look different because they have different shapes and all, right? But they are chemically very similar. We have just carbons and we just have hydrogens. And so a result of that is that they're broken down by the same detergent, right? The same Tide Pod, the OH radical. But the difference is that methane is broken down very slowly. It takes around a decade to remove methane, while isoprene is broken down in a matter of hours. So there's clearly this preferential degradation of isoprene with respect to methane. And so really driving home that point, let's say we start out with a certain amount of detergent, right? Seattle prices are really high. There's a lot of inflation. So you go to QFC, and all your roommates piled up all your money, and you can only afford 8 Tide Pods. And so that might hit too close to home, but bear with me. And so, let's say your roommate, isoprene, is like, I need to do all my laundry before you, and they have a huge load of laundry. And so there's a lot of isoprene, they need a lot of Tide Pods to break it all down, and now you're left with only 2. So there's only 2 OHs left for everything else, including methane, but there's a lot of methane in the atmosphere. And so that methane will just break down less quickly. There's just not enough OH to break it down, which can cause methane to accumulate over time, which can lead to more greenhouse effect. So this is pointing out a really interesting cycle where increased temperatures increased isoprene, which can then increase methane and kind of amplify and reinforce this whole cycle. And so, in conclusion, isoprene hopefully is a fascinating molecule. We've learned that isoprene can worsen air quality, but only in the presence of this fabric softener, right? These nitrogen oxides, which are emitted by cars. We learned that why exactly plants emit isoprene is a mystery, but that temperatures seem to be an important role in governing these isoprene emissions. And finally, we've seen that changing levels of isoprene, perhaps due to this temperature dependence, can alter how long methane lasts in the atmosphere, which can then increase global warming. And so, as an atmospheric scientist, I feel like I always looked up towards the sky to really better understand these super important environmental topics like air pollution and climate change, which is warranted. I mean, a lot of these have to do with gases in the atmosphere and all of the stuff that's happening there. But perhaps some of the answers may have been on the ground this whole time. And so perhaps in research, it is now time to really see the forest for the actual trees. Thank you.